all right. For you. So derivatives today, they become much, much easier to take than they were yesterday. You know, this process of using limits to take derivatives, that gets old. That takes a long time. So we got good stuff for you today. So before we do that though, let's look at this piecewise function here. This is a good question. It says determine a value of m, if possible, for which this derivative exists at 2, which f prime of 2 exists. Okay, let's think about this for a second. What are the criteria that we have to meet for this derivative to exist at 2? What do you think? Okay, the function has to be continuous, doesn't it? Right? Because it's continuous, does that guarantee it's differentiable? Yes or no? Give me thumbs up or thumbs down. Just because a function is continuous, is it necessarily differentiable? Lots of thumbs down. That's good, right? Because we could have, for example, like a sharp corner there, right? Where it's continuous but not differentiable. Real quick, let's just review. What are the places where a derivative doesn't exist? Somebody tell me one place where a derivative doesn't exist. Well, the simple, obvious, say it again. Vertical tangent. Okay, doesn't exist at a vertical tangent. That's some place where the tangent line would have an undefined slope, right? So that's one good example. What else? Asymptotes. Okay, so if we had asymptotes, it could not work at an asymptote. And how could we justify that? Well, the limit couldn't exist there, right? So that's an easy way to remember that one. What else? Cusps. Okay. It can't exist at a cusp, which is kind of and that's sort of a combination of two things. Sharp corner we already mentioned, and a vertical tangent line, right? A cusp would be sort of a combination of both of those at once, a double whammy. And then, of course, obviously a place where the function is, differentiability implies continuity. So to be differentiable, it obviously has to be continuous too. Okay, so then what are the criteria we have to meet? Well, we already said continuity, but what else? It could be continuous but not differentiable if it has a sharp corner. Now, how are we going to get at that without a graph? How are we going to ensure here that not only is it continuous, but it doesn't have a sharp corner? What's our tool in calculus for making sure that that's not happening, that we don't have a sharp corner? I mean, think about what the problem with the sharp... Go ahead, Lily. I'm sorry.
Is it if the limits are equal?
Okay, the limits, we're going to probably have to use limits here, but the limits of what? Right now, think about what a sharp corner is. A sharp corner, we have our new, more highly evolved calculus ants now that have these built-in slope sensors, right? And so the problem with a sharp corner is ants approaching from the left and the right get different readings on their slope sensors. They both anticipate stepping on the same point if the function's continuous. Do you see the problem? So how could we... Well, let's deal with the continuity issue first, and then we'll get back to this one. So one thing that has to be true is the function has to be continuous, and that's a limit issue, isn't it, right? So we know that the limit from the left and the limit from the right have to be equal, don't they, right? So what is the limit of f of x as x approaches 2 from the left is going to be the limit of what part of the function? Top or bottom? Which piece? Somebody just say it out loud. What's it going to be? Top. There you go. Top. So we get the limit of mx minus 16 as x approaches negative 2. Well, we can just evaluate that directly, or approaches 2, right? And that's going to give us 2m minus 16. Okay, well, we don't know what m is yet. We're going to set the value of m, aren't we? What about the limit from the right? That must put us on the bottom part of the function, right? So that's going to be the limit of 4x squared as x approaches 2 from the right. Does it make any difference when I'm evaluating this limit directly? Does it really make any difference if I'm approaching from the left or the right in this case? Because I noticed that just a little bit on the test. People sometimes wanted to put pluses and minuses where you really don't need them. The only place where we really need a plus or a minus when we're taking a limit is with a 0, isn't it? Right? I'm approaching 2 from the left. That just means its values like 1.9999, but it doesn't matter. I'm still approaching 2. If I'm approaching 2 from the right, it's 2.000001. Doesn't matter. I'm still approaching 2. When I directly evaluate, the number that I'm plugging in for x is going to be a 2, right? I don't have to plug in a 2 point something. I'm just plugging in a 2. X is approaching 2. So that's going to give us 4 times 2 squared is what, 16? Okay, everybody agree? So then we could set a value here. How could we determine a value of m?
Say 2m minus 16 equals 16.
Yeah, those two have to be equal, don't they? Right? The limits from the left and the right have to agree. And so I come up with the equation 2m minus 16 equals 16. I can just add 16 and divide by 2, and I get m equals 16, right? So that's the only value of m that we could have that's going to make this function continuous. Are we done? Johan's shaking his head. What's wrong, Johan?
Don't we have to find where it exists at derivative?
Oh, so right. So we still need to know what are the slopes from the left and the right. So our tools, remember, for doing that is we're going to take a limit or a derivative from the left and a derivative from the right. Okay, so what are we going to get here then? If we want to take a derivative from the left and a derivative from the right, this is where we'd have to take some limits. So you know what? I don't want to do that. I'm tired of taking limits. Let's come back to this question in just a little bit after we've got some tools for doing this more easily. How's that sound when we get our shortcuts? Because you guys are probably tired of taking all these limits. I know I am. I'm ready to move on and get a little more efficient with my calculus here. Okay, I tell you what, we'll come back to all these. We'll come back to all these questions and do these after we've got a few tricks up our sleeve. Because right now, if I want to find equations of tangent lines and normal lines, I've got to take a bunch of limits, right? And we've already had a lot of practice with that. So let's go on and let's come up with a shortcut here. What we want to do is, yeah. I am. Let me double check, but I'm almost positive I am recording. I am recording. Thank you for checking, though. Okay, so the ace in the hole here that's going to make this really easy for us is if we can come up with what we're going to call the generalized power rule for derivatives. If I've got a function f of x equals x to the n, where n, and for now we'll take n to be an integer exponent, but actually we won't even have to, we'll take it to be a rational exponent. But even that doesn't have to be true. It could be any number. Then we want to come up with the derivative function of that, just in general. We don't want to have to do it every time. We want to come up with a formula for this, right? So when we're going to build this formula, we have to start from scratch, and we're going to use our limit definition of the derivative because that's the only one that we know at this point, right? So f prime of x in general, remember, is just the limit of f of x plus h minus f of x over h as h goes to 0. And for us, if f of x is x to the n, would everybody agree that f of x plus h would just be the quantity x plus h to the n, right? So I'm going to get the limit of the binomial here, x plus h to the n minus x to the n over h. But how in the world are we going to deal with x plus h to the n, right? That's a mystery. How are we going to deal with that part? Well, let me reintroduce to you, and this goes all the way back. I can't remember if we've talked about it this year or not, but I know we talked about this in Algebra 2. We could leverage Pascal's triangle here to come up with the coefficients that go with our expansion. Let's just do a practice one for a second. With Pascal's triangle, remember how you build that. You start with a 1, and then you're always going to work your way down. The numbers to the left and the right, along the left slope of the pyramid and the right slope of the pyramid are always 1s. And then any interior number we get by adding up the 2 numbers above it, right? So in this case, we get 1s all the way down, and that's consistent with our rules because there is no number up here. So when we add these 2 numbers up, that's a 0 and that's a 1, that's a 0 and that's a 1. I always get 1s down both slopes. But when I start to get into bigger rows like this, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. You get the idea. 4 plus 6 is 10. And you can just build this thing pretty easily that way, right? It's not hard to build. Once we build Pascal's triangle, we can use this, right? The rows of the triangle, we start off with the 0th row, and then we get the 1st row and the 2nd row and the 3rd row and so on. They correspond to the powers of a binomial expansion. So if I wanted to, for example, take x plus h to the 5th, well, then I would come down here to row number 5, and these would be the coefficients of that expansion, right? And remember how this works. The sum of the exponents in each term has to add up to 5 in this case. And the exponential weight is going to shift incrementally in integer steps from all of the exponential weight being with the x to all of the exponential weight being with the h, right? So the first term is going to have an x to the 5th. The next one is x to the 4th, h to the 1, x to the 3rd, h squared, and so on, right? You see what's going on. You probably remember this from a couple of years ago. And then the coefficients. The coefficients are the numbers that the 5th row of Pascal's triangle gives us. So we're going to get a 1x to the 5th plus a 5x to the 4th h plus a 10x cubed h squared, and so on all the way through, okay? So our goal then is, can we come up with a reasonable expansion of x plus h to the n? Now, we could cheat and just use the binomial expansion, the formula for that, but we're not going to. I never remember that. I always have to kind of figure it out on my own, from year to year, just doing a little Pascal's triangle. So we can do that. How could we come up with something like this? How could we come up with, if I go all the way down to the nth row, what am I going to get? Well, we know the first term probably, don't we? I think I can turn the page here maybe. Oops, no, I don't want to do that. What's the first term going to be? Anybody want to hazard a guess? The coefficient's going to be 1. And what's the first term going to be? Then I get a 1 times what? X to the n. Okay, good. Okay, now is where it gets. Now we know what the exponents are going to do, right? The exponents are going to be what in the next term?
X to the n minus 1 and x to the 1.
And h to the 1, right? And then the next one's going to be x to the
n minus 2 and then h to the 2.
and then we're just going to go all the way down. Our very last term is just going to be an h to the n, isn't it? Right? So we got to come up with what the coefficients are going to be, though. So here's where you got to, and I don't want to spend a ton of time on this, but I'll see if you can see a pattern here. Okay. The second number in Pascal's triangle, so the second coefficient, how is that related to the number of the row?
You mean the 6 in the case of row 6?
Yeah, it's a 6, right? So the second coefficient in our expansion would be this diagonal, wouldn't it? Well, look, those are just the natural numbers, right? So they're just equal, right? Whatever the row number is, that is the same value as the first coefficient after the x to the n. Everybody see what I'm saying? So the number that goes here is just going to be an n, isn't it? If it's the nth row, then that first coefficient is going to be an n, whatever n is, right? Okay, the next one's a little tougher. Can you see what the next one's going to be? The next diagonal here, we call these the triangular numbers. How do we get those? And how do we have to be able to derive these numbers from the row numbers, right? Because the row number is what corresponds to the power of the expansion. So for example, how do we get a 15 here and a 10 here? Does everybody see? I'm not going to give you much time.
The way I would probably look at this is I see if you go down the green row, it goes 1, 3, 6, or well, when you add, it goes you add 2, and then you add 3, and then you add 4, and then you add 5. So like the sum of n starting at 2, like the sum thing, and then n scales up from, scale up from 2 and then to whatever, x, well, I guess you'd have to make n something else. But anyway, you'd have a sum function that just keeps adding down the list.
Right, and you could do it that way. You could use like a recursive routine to do it that way.
You just keep adding n minus 1.
Right, so you'd be doing something that's pretty clever. So what Seth's saying here is you could do something like somehow we could come up with a summation, right? We're going to say something. I think this is. Tell me if this is what you're saying. The sum of some term as we go from 1 up to n is going to give us 15 in this case, for example. You just have to figure out what goes in here. Okay. And we could do that. We could do some recursive algebra and come up with a routine that way. I'll give you a little hint on this one. You can also just see this pattern if you look. I don't have to just define it in terms of n. I could even maybe define it in terms of some combination of n and n minus 1, or you see what I'm saying? So how could I use, I'll give you a hint. How could I use the nth row and the value of n minus 1 to always correctly predict what the third coefficient is going to be? Like how is 15 related to 6 and 5? In the same way that 10 is related to 5 and 4.
Keep going up by 0.5. The 2 to the 3 is 1.5, and the 3 to 6 is 2, and the 4 to 10 is 2.5.
Well, there might be a relationship there, but that's not what I'm looking for. There's a simpler pattern. How do the numbers 5 and 6 predict 15, and the numbers 4 and 5 predict 10, and the numbers 3 and 4 predict 6, and the numbers 2 and 3 predict 3? Think in terms of arithmetic operations here, multiplying, dividing, adding, subtracting, stuff like that. Say it again, Emma. Times 1/2.
5 times 1/2 of 6 would be 15.
Okay, so another way of saying that would be we could take the product of n times n minus 1 divided by 2, right? Same thing. See what she's seeing there? 5 times 6 is 30, divided by 2 is 15. 4 times 5 is 20, divided by 2 is 10. Here we get 12 divided by 2 is 6. Okay, that works, doesn't it? That's consistent. So we could say something then for our next coefficient, we could do something like n times n minus 1 divided by 2. And if we want to go, so okay, now using that logic, real quick, I'll give you a chance here to see. I'm not going to give you much time, but see if you could figure out what the next one's going to be. Just kind of a fun little puzzle here. So now we're going to have plus something times x to the n minus 3 times h cubed. So what about the blue? And maybe you can start to see a pattern emerging here. For the second coefficient, we only needed n. For the third coefficient, we needed n and n minus 1. For the fourth coefficient, maybe we got to dig back one more layer, right? Maybe we need n minus 1, and n minus 2. So how could I relate those three numbers to 20 in the same way I relate these three numbers to 10, these three numbers to 4?
Is it n times n minus 1 times n minus 2 over 2 times 3?
Which is 6.
Yeah, 6. And then, you would go, and then it'd be times 4.
Right. So it's going to be, right. So this one was 1, this one was 2, this one was 6, which is 2 times 3. So on the bottom, those are really just factorials, aren't they? Right? I get 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. So we could even start to come up with a more generic formula with this, but we don't really probably need to go any further, right? This is going to be enough. If we think ahead a little bit, why are we doing this? Well, we're doing this because we want to be able to plug something in here for our limit, right? But think what's going to happen in our limit. When we expand this thing out, I've got this minus x to the n here, and we know what has to happen when we take limits like this, right? All the naked terms have to cancel, and I have to be able to factor out an h and cancel the h's. It's always been that way, right? So we don't probably have to go very far with this, right? When I start to take this limit here and evaluate this thing, I only need to go out a few terms, because when I expand this thing, x plus h to the n, well, here's all the terms that we expanded, right? We have an infinite number of terms if n approaches infinity, for example, in between. But look, the x to the n cancels, and I'm left with a bunch of terms that all have various powers of h in them. Okay, so I'm going to need to factor an h out of all of those. When I factor an h out of those, the only term that ends up not having an h remaining in the term when I undistribute one is that first term. All the rest of them, when I factor an h out, they're still left with powers of h in each term. Right? Why is that important? Because we're taking the limit as h goes to 0. So I only have to go in, too deep on this, 2 or 3 deep to see the pattern. And, we know that these h's will cancel vertically. And then when I take my limit as h goes to 0, well, look what happens. All these other terms, there's an h in this term, right? So that one's going to go to 0. There's an h squared in that term, so it goes to 0 even faster. Each successive step along this sum, the terms are just going to 0 faster and faster and faster, right? And so what's the only one left over? The first one. There's our answer, right? That's the only term that doesn't have an h left in it. So when h goes to 0 and we evaluate the limit, all the dust settles. That's the only thing we end up with is that first term, right? So there's our answer. We just did it. There's our generalized power rule is right there. The derivative with respect to x of x to the n is n times x to the n minus 1. That's hugely valuable, right? Because we didn't specify what the exponent was. We left it totally general. And of course, I could have, if I wanted to, I could have included a constant in my function. And this proves another valuable point about differentiating stuff, about taking derivatives. If I were to have put a c in there, what would it really have changed? I just would have ended up with a c being multiplied by each of these terms, right? I have a c times x plus h to the n minus a c times x to the n. Let's factor that c out front, and everything else looks exactly the same. So when all the dust settles, if I include this constant, I just get a constant times my result of n times x to the n minus 1. So in general, that tells us something pretty important about what we can do with constants when we differentiate. As you might have expected, we can pull that constant out in front of the derivative and not even worry about it, right? So when we want to do something, and we'll get some practice with that today. Okay, but here are our two important rules then. Really, this is the only one that's important, and if C is 1, then it becomes that rule, right? So let's practice this. Let's practice a really easy one first. Maybe let's yeah. Let's do this. So what if I give you f of x equals x to the 12th? What's my derivative function going to be? What was it again? Derivative of x to the n is n times x to the n minus 1. So I'm just taking the exponent down in front, and I'm subtracting 1 from the exponent. Yeah, so this just becomes 12x to the 12 minus 1, so 12x to the 11. Okay, what happens if I have f of x equals 3x to the 4th? F prime of x equals, well, what about that 3? The 3 I can just leave out front, right? So what's the result going to be if I differentiate this one?
12x to the 3rd.
Yeah, I'm going to get 3 times 4x cubed, but we wouldn't write it that way. We would just write it as 12x cubed, right? Everybody get the idea? Okay, that's our generalized power rule. So now the trick with this is we want to use this as much as possible because it's so easy to use, right? So what about this? Looks different. Y equals 2 over x. That doesn't look like it fits our template up here, but it does if we pre-write it. We always want, when we say pre-write it in calculus, kind of something I say in calculus, that means we want to rewrite the function in a way that makes it compatible with the power rule. So how could I rewrite the original function? So pre-write the derivative so it'll fit this.
2 times x to the negative 1.
There you go. It just becomes 2x to the negative 1, doesn't it? And now I can apply my rule. So Kyle, what am I going to get if I differentiate that?
I don't know.
So I'm going to use just using my rule, right? Here's my rule up here. The 2 we just forget about. We're just going to, that's just multiplied by our answer. What's my rule for x to the negative 1? I take the exponent out front and subtract 1. So what am I going to get?
X to negative 2.
Right, but then I got the negative 1 I have to put out front. So I'm going to get a negative 2x to the negative 2, right? And then if I want to write that without a negative exponent, it's just negative 2 over x squared. Okay, everybody give me thumbs up, thumbs down, thumbs sideways on that. Okay, let's try another one. So, we want to always rewrite these in a form where we can use this derivative form. This is probably the easiest one or one of the very easiest ones we'll ever apply. So it's one we like. Okay, what about this one? It looks like we've got some kind of a quotient going on here. But what's the important point about this one? What's the answer here? Somebody want to tell me?
8/5 t.
Yeah, right? Because the 4/5, and maybe it was like, well, why is he even putting this one up here? So the 4/5 is just a constant, isn't it? So it's just going to be 4/5 times the derivative of t squared. So that's 4/5 times 2t, 8/5 t to the 1, right? But we don't write the 1 there. There's an invisible 1. Okay. How about, okay, I've got one for you. Let's get rid of the 6. What's that one?
Wouldn't it just be 1?
It's 1, isn't it? Right? Because if there's a 1 there to start with, I'm going to get a 1 times x to the 0, and x to anything to the 0 is 1, isn't it? So the answer is 1. Okay. If I put a 6 out front, then it would just be 6, wouldn't it? Oops. So another way to think about that, if we use a different notation, you can see how that's compatible with this other notation. What if I do the derivative with respect to x of x? Right? That's a notation. That just says differentiate whatever's inside. The derivative of the function x is what? Well, we could think about that as being the derivative of x. That's just dx over dx. So the algebra works. It just turns out to be 1. Okay? Either way, we get 1. Okay, let's go one step farther with that. How about if we do... How about that one? Oh, sorry. I don't mean f prime. I mean f. What's that going to give us? We could think about this in terms of a graph. It's 0, isn't it? We could think about it in terms of a graph. If the function is f of x equals 5 or y equals 5, look, that's just a horizontal line. What's the slope of that line everywhere? 0, isn't it? Right? And that's what the derivative function tells us. But we could even play a little game here to show that it's consistent with the power rule, right? Because if I bring that exponent down front, 0 times 5 is 0 times x to the minus, it doesn't matter, right? I get 0. Okay. All right. What about that one? What can I do with that? Let's see, Natalie. Any ideas how I could use the only rule that I know right now, which doesn't have any square roots in it?
I don't know.
Okay, so I got to be able to write this as some with an exponent. Madeline, you got an idea?
Wouldn't it be like x to the 1/2?
Okay, so 2 times x to the 1/2. Power rule still applies. So what's that going to give me if I differentiate then? Go ahead, Madeline.
I don't know.
So we're following the same rule we always do, right? We're gonna take the exponent and that becomes the coefficient, and then subtract 1 from the exponent with the power rule.
Would it be x to the negative 1/2?
Yeah, everybody agrees. So 1/2 times 2 is 1. That's my coefficient, and then 1/2 minus 1 is negative 1/2. So I just get, in this case, 1 over x to the 1/2, which is 1 over the square root of x. Okay. Okay, how about this one? The derivative with respect to x of all this stuff, how could I rewrite the argument of that derivative? in a way that's going to work with the power rule. What do you think there? Andy, what am I going to do? How do I deal with something like that? X to the cube root of x squared.
Would it be x to the 2/3?
Good, and it's on the bottom, so what does that make it?
It's negative.
Okay, so I'm going to get a 1/2 x to the negative 2/3. So then I can do this. I can take this derivative just using, here, you guys can't read that, can you? So what am I going to get, Andy, if I differentiate that then?
Well, you get negative 2/3 times 1/2.
So that's negative 1/3.
Mm-hmm. And then you get negative 2/3 minus 1.
So what's that?
Negative 5/3.
There you go. Okay, so I could write that as negative 1/3 x to the 5/3. And if I want to use radicals, I could go 1/3 times the cube root of x to the 5th, right? Okay, the trick being we just got to be able to write it as a power. All right, so let's go back and let's tackle, one other thing maybe. So what about this then? Does this look hard? What do you think I can do? I'm not going to prove this one to you, but what do you think I can do if I've just got a string of a bunch of terms that are added up and I'm differentiating? And rather than give you a rigorous proof, just think what we did with limits, right? Because the derivative is based on taking a limit. So what do you think? Emma, what do you think? How would you think you get an answer from this one?
I have no idea.
Okay. Ember, you want to take a stab at it?
I'm not sure either.
Okay. Anybody?
Can you just take maybe you can take the limit of each term, so can't you just do the power rule for each term?
Yeah, that's it. So what we'd say is we're just going to differentiate term by term. If I were building this big complicated function, I had to take a limit of f of x plus h minus f blah, blah, blah. Well, in each of those limits, I could just break those up into 3 separate limits inside the algebra, couldn't I? Right? I could parse that out. So I'm doing 3 separate limit problems, which means I can just differentiate term by term. I don't want to take the time to show all that to you, but just kind of take that one on faith. Think about it a little bit after class, maybe. So then this first one, what would I get? Well, there's just a 4 there. So I bring the 4 down front. Negative 4/2 is negative 2 x cubed. No big deal. Here we're going to get 3 times 3 is 9x squared. And we already did this one. I've got x to the 1/2. So I'm going to get minus 1/2 x to the minus 1/2, which is just x square root of x on the bottom. Okay, so we just differentiate term by term. Okay, so let's go back then. And now that we've got our little trick, let's finish up the problem that we started with. This makes it a lot easier, doesn't it? Now, if I wanted to come up with a derivative function here, we could write a piecewise function for our derivative where we're just going to differentiate each piece of that piecewise function, right? So when x is less than 2, f prime of x is just going to be the derivative of this top piece. Well, what's the derivative of that top piece, Andrew?
X, or not x, just 1.
Not 1. The derivative of 16, that's a constant. So the derivative of a constant is 0, right? So that one's going to go away. But what's the derivative of m times x to the 1?
Just m.
Just m, right? That's just going to be m. So on the top, we're going to get m. What about on the bottom? What's the derivative of 4x squared? 8x. Okay, and it's 8x whenever x is greater than 2, but we still don't know if the derivative is going to exist at 2 because it might be a sharp corner. Well, we already determined that the only way for this function to be continuous, we were already constrained. M had to be 16. So we just have to see, does 16 work if I plug it up there? So if I evaluate this thing at 2, right, according to this function up here, if the derivative exists, would you agree that f prime of 2 would equal 16? Right? 8x, everybody agree? Does it work? Do we get 16 from the left and from, yeah, we do. If m is 16, that works, doesn't it? Right? How would we say that? Well, we could say the derivative from the left okay, is what? Well, the derivative from the left is m. The derivative, and that's f prime of 2, right? So we're going to do, hey, let's do it this way. We can make this a little bit, that's kind of cumbersome to write all that stuff out. Let's make this better. So f prime of 2 minus is m. F prime of 2 plus is 8 times 2 is 16, and so it works. That's a pretty sophisticated problem. I couldn't even find any problems like that in all the college texts I was looking at for one in the assignment. I couldn't even find one. They're just, I guess it's too hard, but it's not that hard, right? Give me a 1 to 5 on that. Okay. All right. That might be something to go back and revisit. Okay, what about this? Find the equations of the lines tangent and normal to the graph. Now, this would have been a long problem yesterday. Today, it's not that big a deal. We can come up with a derivative function right away. So how would I maybe have to rewrite this, Isaac, for us to be able to use the power rule?
I'm not sure.
X, that doesn't look like a power. How could I rewrite 1 over x as a power? X to what power?
-1.
-1. There you go. Good. Okay. So now I could differentiate that. The derivative of x to the 1 is just 1. Derivative of x to the -1 is minus x to the -2. Right? That's the same as 1 over x squared. So there's my derivative function. Okay. And we're trying to find, oh, what happened here? Oh, I got cut off. I don't know why. So find the equations of the lines tangent to and normal to the graph of f of x at, we got to pick a value. Let's just make one up. We'll just say at x equals 2. How about? Yeah, we'll pick 2. Okay, so how would I find the tangent line then? At x equals 2. What are the ingredients for a line? Lily, what do I need if I want to come up with the equation of a line? Going back to algebra 1. Okay, I need a point. Let's do that first. So if x is 2, what's my y value going to be?
Wouldn't it just be 0?
No. No, if I want to find the y value is going to be the function spits out, right? F of x equals y. So if I want to find out what goes here, I'm just going to do f of 2. So I'm going to get 2 plus 1/2 gives me 5/2. So there's my point of tangency. What else do I need? Do I need a point? And what else, Daisy? To come up with the equation of a line.
Slope.
I need a slope. Yeah, and that's where the derivative comes in, right? The slope of the tangent line is going to be the value of the derivative function at 2, f prime of 2. So what's that going to give us? That's going to give us 1 minus 1/4, right? So we got a slope, we got a point. We should be able to come up with this pretty easily then. We just use the point slope form. So y minus 5/2 equals m times x minus 2. And then it's always the same. I distribute and add 5/2 and we get it. Well, and there's the equation of the line, isn't it? I mean, we're done. But if we wanted to put it in slope-intercept form, we would just end up with 3/4 x minus 3/2. And then we're going to add 5/2 to both sides to get rid of that. Right? And so we end up with y equals 3/4 x plus 1 minus 3/2 plus 5/2. So there's the equation of the tangent line. What if I wanted to come up with the normal line? What's the only difference? Really, I've done all the work. If I want to come up with the normal line, I still use the same point because the point of tangency is the point of normalcy, right? That's the point where the normal line is just where the line is perpendicular to the graph at that point. What's the only thing I have to change? What's the slope of the normal line, the perpendicular slope, going to be?
The inverse of that.
The reciprocal, you mean, right? So, but not just the reciprocal.
The negative reciprocal.
There you go. Good. The opposite reciprocal. So we would just use that slope instead when we use the point slope formula, right? Okay, one more. This is the one I really wanted to get to. Oh, actually, there's 2 more. This is a good one too. So find an equation of the line that is tangent to f of x and parallel to the given line. Think about that one. There's a lot going on there. Oh, I only have 1 minute left too. That's very disappointing. I would so like to do that problem. I'm sure you guys are deeply disappointed too, and you're going to have to wait 2 days. It's actually 3 days now. You get a day off tomorrow. But you guys, maybe you want to just come in tomorrow and we'll just do a calc class tomorrow. What do you think? Let's take a class vote. Thumbs up, thumbs down on. I don't think I can do it. I know you wish I could. Okay, so we'll see you again on Friday. I will put a little assignment up over this too that you can get started on, but we still have a few things probably to go through. But you can get a good start on it. All right. Have a great day. Maybe I'll see you after school if you want to test, etc.